Hi again. This lecture is about expectations, specifically about expected values or expectation values of random variables and of functions of random variables. So we'll spend a fair amount of time just giving the definitions of these things and showing how to calculate them for the discrete and continuous cases. And we'll do some examples as well. And we'll finish off the lecture by introducing how these things are used or how they relate to the concept of independent random variables. Okay, let's get started. So expectation values are used in the following context. So suppose you have some random variable, it could be discrete or continuous, and we'll call it x. This variable can take on a number of values, right? Some specified thing, take on various values. And the expectation, or sometimes called the expectation value, tells you something about, it's literally what it says. It tells you something like what value you should expect it to take on. So we say, we introduce what we call the expectation value, or we write it in this funny way, the expectation value of x, or the expected value. Sometimes it's called that, or expectation value. Of x. And it should become more clear. We're going to really work through quite a few examples to try to make this clear. And so we'll go straight to this more formal definition now. So we're going to define it. But this definition is going to be a little bit on the long side, because we're going to have to kind of make one for continuous variables and one for discrete variables. So we'll work with the discrete variable first, right? So this is the discrete case. So that's just the first one. And so it works like this. So we say, okay, if x is a discrete random variable, and it takes on values following value. So we'll say it can take on value x1 or x2 and so on up to xn. But here we're saying xn, but it could be the case that n is infinite. So n equals infinity is okay. That's a possibility. And we'll suppose that it has a PMF that we know. Probability mass function, and we'll call that f of x as usual, right? Then the expected value is as follows. The expected value of x is equal to, it's a sum, I equaling 1 to n, of xi times f of xi, right? So I'm going to highlight this whole expression, because this whole expression is kind of our definition, really. That's the expected value or expectation value in the discrete case. Now, before I carry on, I want to make a couple of comments. All right, so this is sort of an aside within the definition, if you will allow it. All right, so I'll make a little note. There's two things I want to point out. So the first thing is I want to try to make sense of this equation that we wrote down and see why it's sensible. So if you make, let's say, just for the sake of argument, you have the following. Let's suppose that f of xi is equal to 1 over n. Now, that's obviously not possible if n is infinity, partly because it becomes 0. Well, I guess then it's okay. But this is meant to be for a case where n is finite. It's just an illustration, a little thing I want to make a note of. So suppose that f sub xi were 1 over n, so that means that each of the values of x is equally probable, and it has probability of 1 over n, right? So that's this thing here. Then, if you look at this, so that's for all I values. Then, if you look at that equation for a while, the expected value of x should look somewhat familiar. It's just the average of the x sub i's. Or the mean. The average or the mean of the x sub i's. And so if it's not the case that the probability mass functions are just a constant and 1 over n, then what you have is what you might call like a weighted average, where the probability mass function gives different weights to the different values that can be taken. But so I wanted to make this note just so that it's sort of clear why this is a sensible definition, or why it somehow fits with things you might be familiar with, why the language kind of works. Okay, the other thing I want to comment on is very similar to averages as well. So notice that the expected value of x, it doesn't have to be one of the possible values that x can take. It's not required, or it's not necessarily not required to be one of the values or one of the xi's. Right, and so here you can think of lots of common everyday examples, like if somebody says the average number of children per family is 1.7. That doesn't mean there's any family with 0.7 children or 1.7 children, right? It just means, it's the average. And so the expected value of x doesn't have to be one of the x sub i's, right? So I just want to make that point. Okay, now we'll make the definition for the continuous case, and it should be a little more understandable, or it should be a little better motivated after having seen the discrete case, right? So I'm going to make the continuous case. So this is probably too much wordiness in a definition by mathematician standards, but what the heck. All right, so we'll say if you have some continuous random variable y is a continuous random variable with a known PDF, and we'll call that f of y and hope that the context makes it clear that this is not the same function as we just wrote down before. Then the expected value of y has the following form. It's the integral from minus infinity to infinity of the value y, little y, times the probability density function y times dy, right? And so here you should be able to make sense of this, because the probability density function times the little differential dy, that's an infinitesimal probability, right? So that's the infinitesimal probability somehow associated with the value y. So it's the probability of y being in some infinitesimally small range. Okay, and so that's the expected value for the continuous case, and I'll highlight that one as well, because it's kind of a definition here. Yeah, so let's just dive straight into some examples and kind of see how these things work. Right, so I'll just take a pause there and let you look at the two things right next to each other. It should be sort of sensible what's going on here. Okay, now let's go to some examples. So we'll do an example. And in this example, we're going to say, suppose you have a discrete random variable, x, and it's Bernoulli distributed with probability of success, p, probability of success. And I just want to find the expected value. Right? That's pretty straightforward. So here, it's a really simple process. In fact, it's so simple it almost gets a little confusing. But so what is the probability mass function for a Bernoulli distributed variable? Well, there's only two possible values it can have, right? So we'll say, here's the PMF, f of x. And so that's equal to the probability that x is equal to little x, right? That's what the PMF is. So it's going to have two different values. And over here, I'm going to make the different values that x can take on. So it can take on two different values. So it can take on the value 1, which we call a success. It's just a name. And it can take on the value 0, which we call a fail or a failure. And so the different probabilities are, it's P is probability of success, so not surprisingly, that's there. And the probability of fail, then is just 1 minus P. Right? So then the expected value, all right, you just do the sum manually, right? So the sum is, let's go back up there and take a look, right? So we've got, each term has two different things. The value that the thing can take times the probability that it has that value. And then you go to the next term. So we'll go over here. So the value that the thing can take, so 1, that's for success, times the probability that it can take on that value, so that's P. And then you go to the next term. Maybe I should have done these in the opposite order. I think that's traditional, actually. The value that the thing can take, 0, times the probability that it can take on that value, and that's 1 minus P. Of course, that whole term is 0 because it's multiplied by 0. And so this is just equal to P. So the expected value for a Bernoulli distributed random variable is P, the probability of success. Now that might seem kind of an odd thing, I don't know, or maybe it seems perfectly natural to you. But yeah, so that's the expected value for a Bernoulli distributed random variable. And if you look up online all these famous distributions that we've talked about, for each one, you'll find the expected value listed somewhat prominently, usually. Okay, we'll do another example. This is going to be a continuous random variable. So for this guy, we're going to say, let's say y is a continuous random variable. But this time, we're not going to use a famous distribution of ours. We'll make up one with the following PDF. Call it f of y. As usual. And f of y has this form. It's equal to, it's a piecewise defined thing. And in one region, it's going to be given by 2 over a squared times a minus y. And that's in the region where y is less than or equal, or y is in between 0 and little a. And then otherwise, if y is outside of that region, it's 0. I'm going to move this down a little bit. It's a little bit crowded. Right? Now, let's just draw a quick picture of this so you can kind of see what it should look like. So let's say this is the function f of y. And then this horizontal axis is y. Right? So where is the x and y intercept on this, or the vertical and horizontal intercept? So when y is equal to 0, so that's the vertical intercept, this thing has value 2 over a, right? Oops. Over a. And when f is equal to 0, well, that happens when y is equal to a. So it's over here. And so the distribution looks something like this, right? And you should be able to see that area underneath that curve is in fact 1, right? Everywhere else it's 0. So I should use a different color probably, but so like down here it's 0, and anything over here is 0, and so on. Yeah, so that's what our probability mass function looks like. Or sorry, probability density function looks like in this case. And so it's so here A is a constant, but it's any constant. I guess it has to be a positive one. Let's see, what do we have to make sure that this is always positive? Yeah, it just has to be that A is positive. Yeah. So then this thing works. All right. And so we'll just find the expected value. So that's the task. And you should be able, you might want to take a look at this before you actually do it, right? So sort of stare at that distribution for a while, and think to yourself like, well, where is the expected value? Where should it be? It's certainly not at like 3a or something like that. Like, so it's not over here or anything like that. And it's not to the left of the origin. It's not over there. So it's going to be somewhere in this region here. The highest of the probability density values is right above here. But then there's all this other stuff over here. So it's somewhere in that region. That's what we should expect. It's good to look at those things before you start cranking on these problems to make sure you understand. Make sure you can do like a check of whether or not your result makes any sense and so on. All right, so let's just go ahead and do the calculation. So the expected value of y is, as we said, the integral from minus infinity to infinity of f of y dy. Oops, I skipped a thing, right? It's that thing times y. And you might say, well, you don't have to go from minus infinity to infinity. And that's true. That's going to show up right away because f is only non-zero in the region between 0 and a. So that's very quickly going to become integral from 0 to a. And then we'll put in the functions. So here's y. And the function f of y is 2 over a squared a minus y, and then dy. So that's the integral we want to do. It's a relatively easy one, but let's just go about it slowly. So we'll bring out the 2 over a squared, and we have integral from 0 to a, and now we have a times y minus y squared dy. And both of these integrals should be somewhat familiar to you, so we'll just do those kind of in our heads a little bit. So the first one is the integral of ay is 1/2 ay squared. And so we'll put the limits here. You can check that by differentiating it. And then the second one, the integral of that is 1/3 y cubed. Again, you can differentiate it to check it. And so that's 0 to a, like that. Right, so we clean this up a bit. That is to say, we evaluate the limits there, and what we get is 1/2 a cubed. Oops, whoa, 1/2 a cubed minus 1/3 a cubed. And this simplifies to 1/3 of a, or a over 3. And so that's the answer for that one. Okay. Now I want to talk about expected values of functions of random variables. So expected. Expected values of functions. Long title there. And this is not going to require a new definition. We can kind of just carry on with what we had. Move this over a bit. I always tend to drift over there. So we don't need a new definition or anything to work this out. But so let's just say what we're doing here. So let's say, let x be a random variable. and let's say you have another random variable, z, and it's some function of x. Right? It could be like a constant times x, or it could be, I don't know, all kinds of different things. So that's another random variable. Right? And then we want to try to find what is the meaning of the expected value of z. Right? Or in other words, the expected value of g of x. Right? So it is, I'm going to need two different cases. Right? So we'll first write out the discrete case, and then it should be straightforward what the continuous case is. So for the discrete case, and this isn't really a new definition. So what we're going to do is we look at this thing, so we say, okay, expected value of z, also known as expected value of g of x. Right? So that's equal to, I should have, yeah, so in the discrete case, I have to specify, what do I mean? What exactly is meant here? So I'm going to say, in the discrete case, let's say that x takes on values and we'll label them x sub I. And let's just say where I is in some kind of set that I'll call capital I. There's a whole bunch of different, maybe it's 1, 2, 3, or I don't know, 2, 4, 6, or a whole bunch of different values of I that it can take on. Okay, so now back to the story here. So the expected value here, it should be the sum over all the possible values of I. So I'll say all the I's in the set I. And then there's like two things going on here. So the first term should be the value of z. So I'm just kind of sketching how this should look when x is equal to xi. Right, so that's the first term. So that's like the value of the function g of x times the second line down here, carrying down there, the probability that, now I should say the probability that z is equal to the value of z when x is equal to xi. But that's the same as the probability that x is equal to xi, right? Because if x is equal to xi, then z is equal to the value it has when x is equal to xi. I hope that makes sense. So that's how this thing looks. And if we write it down in terms of things we've got, right? So it's the sum over the I. Oops. Fix that. Oh. And so the value of z is then g evaluated at xi. That's the value of z. And then just times the probability mass function for the xi's. Like that. And so that's how this looks. That's how the expected value of a function looks in the discrete case. Right? So now let's look at the continuous case. And you should be able to see this isn't any new definition. It's really just carrying on with the old one, but just kind of putting it in a new context. Okay, so then the expected value, in this case, we're going to say x is a continuous random variable. Right, and then the expected value of z, also called the expected value of, g of x. This is going to be an integral minus infinity to infinity, and then the same form, g evaluated at x, and then times the probability, or the infinitesimal probability for this little range, f of x dx. Right? Okay. Now let's give this a try. Right? See if we can put this to use. All right, so let's make some examples. Another one. All right, so this example, I'm going to say, I'm going to use a discrete random variable. All right, so we'll say x is a, oops, man, writing's getting sloppy here. Not that that's new, I guess. X is a discrete random variable with values and PMF as follows. So let's write them out. So this is just a sort of a made-up case. So it's going to have indices I. So there's going to be 4 different values. So I'm going to label them x sub I. But here's 1, 2, 3, 4. And the different values it can take on, x sub I, are like this. So that x is going to take on value -1. So that's one of the possible values that x can take on. 0, 1, and 2. These are just made up, right? And then the probability that it takes on these values is as follows. So it's a half, a quarter, 0.15, and then the only amount that's left to make sure that we obey the honesty condition is 0.1. Okay, so that's just some made up case where you have a discrete random variable that can take on 4 values with 4 different probabilities. And let's do 2 different things, right? So we're going to try 2 different things here. So first, I want you to find, or I want us to find, the expected value of x. So we'll just go ahead and do that first, all right? It's straightforward. So we'll do that. The expected value of x is equal to a sum. Actually, I'm not going to write the sum, right? It's just so straightforward. There's only 4 different things. Well, maybe I should. No, let's just do it. Right, so just write this thing manually. So you put the value of x times the probability that it has that value. And then you do that for each term. So we've got -1 times a half plus 0 times a quarter, but I'll just leave that off because it's nothing. And then plus 1 times 0.15. And then plus 2 times 0.1. And so, sorry, there's a lot of mixed notation there. So we've got -1/2 plus 0.15 and then plus 0.2. And if you add those things together, you get -0.15. Right, so that's the expected value of x. All right. And then I want to do part 2. I want to find the expected value of x squared. So that is to say, not the square of the expected value of x, but the expected value of the square of x. Right, those are different. Or maybe they're not. Well, we'll see. We'll see. Right, so that's what I want to do now. So the expected value of the square of x. So the procedure is the same, right? We put the probability, we put the value itself and then times the probability that it takes on that value and just cycle through all the things. So I'm going to put that thing on the top of the screen there so you can see it. So the value itself, -1, so I want to square this though, right? Times the probability, so that's a half. Plus 0 squared times a quarter. Okay, but I'm going to leave that off because it's 0. Plus 1 squared, I may as well write it, times 0.15. And then plus 2 squared times 0.1. And if you add all these together, you get 1.05. Right? You can check that. All right, now I want to pause and just point something out. So it's important to see. So notice, this is an important thing. Notice, the expected value of x squared is not equal to the square of the expected value of x. Right? 1.05 is not the square of minus 0.15. So that's an important point. And it's important enough that I'm going to kind of make a little highlight of it, right? It's not to say that it is never the case that inequality becomes an equality, but it is not generally the case, right? So it certainly would be the case like if the expected value of x was 1, and if the expected value of x squared was also 1 somehow, then that would be fine. But it is generally not the case that I forgot to add on my got so excited about the point I was making. It's generally not the case that the expected value of x squared is the square of the expected value of x. That is not usually the case. Okay, so now we go on to our next example, a similar thing, but with a continuous random variable. I'll go back to my regular highlighter. So we'll say y is a continuous random variable with, again, some kind of made-up PDF. And we'll just write in here f of y is equal to the following. So in some region it's going to be 3/8 y squared, and that's in between 0 and 2. So that's for y in between 0 and 2. And then elsewhere it's going to be 0. Okay. And now let's just, again, it's a good idea always, if you can, to kind of plot this, the probability density function, see if you can understand, see what you expect to find. See what you expect of your expectation values. Oops, didn't mean to make that so straight. It's fine though. And so this is y, and this is going to be the PDF probability density function. And so let's look again at the intercepts. So what does this thing look? So let me draw it with a different color. So it's 0 everywhere. Whoa. I always forget. Change the color of this guy. So it's 0 everywhere out here, right? And then when you hit the origin, it takes on it goes like y squared, right? And then it stops when you get to y equals 2. So this is 2 here. And then it's 0 everywhere else after that. And let's see, so what is this height here? This height is 3/8 times 4. So that's 3/2. Like that. Okay, and I might not have gotten the curve exactly right, but that's how it should look. And so you should be able to look at this and ask yourself, like, where do you think, where is the expected value? Like, where do I expect to find y? And so maybe it should be somewhere, I don't know, sort of over in this region here. Oh, you know, I forgot to verify that the one we looked at before was actually in the right place. So let's go back and do that. If you'll give me a little leeway here, maybe you already did it. So this guy, we had this distribution before, and I talked about like the range. I expect the expected value to be somewhere in there, and the expected value was a over 3, right? So if you go over here, so it's a third of a, yeah, and so a over 3 is, oops, so what is that? That's about here. Oops, right? And so that looks good. It seems plausible. It's somewhere in the middle there. It's not meant to be halfway. It's a third of the way over. Okay, so sorry about that. I meant to say that when we did it before. All right, so one of the advantages of doing this online, I have all the notes. I haven't erased it on the board or anything. And so in this case, I think that the expected value will be maybe somewhere on this edge of things. Yeah, so let's go ahead and do the calculation. So the first thing we're going to do is calculate the expected value. All right, so part 1, find the expected value of y. All right, and so we'll just dive in. So the expected value of y is equal to an integral, as usual. and then we put the value of y times the probability density function, dy. And then this integration is going to be 0 everywhere where the probability density function is 0. And so this becomes the integral from 0 to 2 of y times 3/8 y squared dy. So in other words, kind of making a mess here, 3/8 times the integral of y cubed over the range 0 to 2, right? And so that's an integral that should be fine for everybody. So that's 3/8 times 1/4 y to the 4th, and again you can check that by differentiating it 2 to 0, or 0 to 2, sorry. And so then if you substitute in the 2, right, you get 16. So 3/8 times 16 over 4, and then if you tidy this up a bit, it's 3/2. So let's look back at the picture and see if it's in a place we expect. So it's a 3/2, so 1.5, right? And so that is somewhere, so let's see if that's 2, then 1 is here, and 1.5 is around there. Yeah. So, here, let me do this. So it's somewhere around here. And that seems okay. That seems like kind of what you might expect of your expected value. All right. Okay, now the next part, part 2, we'll find another expected value, but a function of this guy. So I want to find expected value of 1 over y. Right? So I'm just going to dive right in again. So expected value of 1 over y is equal to the same integral, and I'll just skip some steps, right? We know it's only going to end up going from 0 to 2, and I'll put in the 1 over y here, and then I'll put in the PDF, 3/8 y squared dy, right? And so we can carry on with this integral, 3/8 integral from 0 to 2 of y dy. And so this is 3/8 1/2 y squared from 0 to 2, which is 3/4. Right? So that's fine, but I want to make another note, just like we did before. So notice the expected value of 1 over y, sorry, that's pretty clumsy. Let's rewrite that a little more carefully, sorry. So the expected value of 1 over y is not equal to 1 divided by the expected value of y. It's not like, I don't know why I say, sometimes it's weird to teach by contradiction like this. I don't know if I want to instill the idea that you would have done, that you might have had that idea. Like, that isn't true, and so why am I telling you about it? There's lots of things that aren't true. Nevertheless, so over here, just like we saw before, the expected value of x squared is not the same thing as the square of the expected value of x. And then here we see that the expected value of 1 over y is not 1 over the expected value of y, right? So it's not 2/3. Yeah, and so I'll highlight this again because it's kind of important. It's only important really if you had that idea, which, you know, when you get anxious on an exam or something like that, sometimes these kinds of things happen. You're like, I'm just going to try this. This sounds promising. I've certainly done that before. Okay, so now we'll finish off with just going over some properties of expected values. Some general properties. And we'll prove one of them, but the most of them we won't. properties of expected values. So these are going to be like generic properties. Okay, so the first property is the following, and then we'll prove it. The expected value of ax plus b is equal to a times the expected value of x plus b. Now here, a and b are real numbers, and x is a random variable. It can be discrete or it can be continuous, and this is fine. So there's some sort of linearity to the expected value operator, and that should make sense because look, oh, it's way back here. I probably shouldn't have gone all the way back. The definition of the expected value here, so this is the continuous case. It's sort of linear, right? It's an integral, and so much like derivatives and integrals can be passed around in some linear way, it turns out that this is going to be fine, and so we'll prove that. Right? We'll do it for the continuous case, right? So proof. For a continuous case. And the proof works just like you might, I think, maybe you would imagine, but maybe not. So let's go through it. So let's say, okay, x is a continuous random variable, and it has a PDF that we know. This PDF, f of little x, right? Then what is the expected value? We're going to use this thing that we've seen before, of g of x. Right, that's equal to the integral from minus infinity to infinity of g evaluated at x times f of x dx. Right? So now we want to work on this case where g of x is ax plus b. Right? So let's say let g of x equal ax plus b, and I'm not going to, so you know a and b are real and so on. So okay, so let's just try it. So the expected value of ax plus b, using that expression there, it's the integral from minus infinity to infinity of ax, little x plus b times f of x, right? We don't have to say what f of x is. We can do this proof all by itself. All right, and so this is a times the integral from minus infinity to infinity of x times f of x dx, don't forget the dx, plus b times the integral from minus infinity to infinity of f of x dx. Right? Now, these two things that we've just created should look familiar, right? So what is this thing here? If you look at that, so it's the integral of the value times the PDF evaluated at that value. So that's the expected value of x. And what about this thing here? This is an old friend. So it's the integral everywhere, all the area under the probability density function everywhere, right? So that's 1. That's the honesty condition right there. If that's equal, saying that that is equal to 1 is the honesty condition. Okay, and so that's what we were trying to prove, right? So we've got, so this is equal to a times the expected value of x plus b, which is what we were trying to prove. So that's only proving it in the case of a continuous random variable, but you should be able to prove it for a discrete one basically the same way. So I'll leave that one to you. The discrete random variable proof I'll leave to you. So this is one of this property up here. I should probably highlight it. It's kind of important. Right, so that's property number 1. And then property number 2, we're only going to see 3 properties here. Property number 2 is that the expected value of x plus y, where both of these are random variables, is equal to the expected value of x plus the expected value of y. So here x and y are random variables. Right? So that's the second property that I would like to declare. This one I'm not going to prove. You prove this in a problem set in week 10. So proof, I think you're just asked to prove it. You could probably start working on it now if you want. It's in week 10 problems. I don't think it's one of the assessed things. It's one of those bundles of unassessed problems. Okay, and then I'll just point out so you can extend this, all right? So this can be extended. This extends to a big sum, right? Let's make xi, sorry, hang on. x1 dot 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 up to xn. Let's make those all random variables. Then it is the case that the expected value of the sum of those is actually equal to the sum of the expected values. So you see, this is why we kind of had to say before that those I made those kind of warnings or cautions before, because it does turn out sometimes the thing just gets, the expected value operator, if you will, just gets distributed in this most natural way. Okay, so again, we'll do that proof, the proof of this one at another time. And then the third property that I want to talk about, we won't be able to prove this one today, but I'll sort of tell it to you. We'll prove this much later in the next chapter. So let's say we have 2 random variables again. If x and y are, now this is important, independent. Random variables. Right, so this is so important actually that I'm going to underline it in red and put a star next to it, because these other 2 properties are generic, and this property is true and it's generic, but it's true when it's a statement that's useful when 2 random variables are independent, and I don't want you to forget that. It's crucial. So if that's true, then the expected value of their product, x times y, is equal to the product of their expected values. Right? But it's only true if the 2 variables are independent. And in some ways, actually, I mean, in a way, so this is almost like the definition of independence. And we'll come back to this later. All right, we'll see this, we'll see it, so we'll see the proof and kind of more discussion about it in chapter 5. The notes actually say it's in chapter 4, but that's where we currently are. And it's not in this chapter, it's in the next chapter. Okay, and then again, this also extends. So this extends. If you have a bunch, if you have x1 dot dot up to xn, and those are all independent, random variables. So again, it's super important that you remind yourself that they're independent. Otherwise, this just doesn't hold at all. Then the expected value of the product of all of them is the product of the expected values. So let's write that. expected value of the product of the xi's is the product of the expected values. Like that. Okay, I hope that lecture met with your expectations. You should be pretty good with expectation values by now. You'll have a lot of practice with them in the problems that we assign. And I'll see you next time. Bye.